Good morning and welcome back to the new session. In the previous class, we were discussing about the layout of resistive load, and we also discussed how this resistive load works. And it's various possible combinations, like how we can enhance the noise margin and other things. Okay, so let us try to see one more configuration in detail, and that configuration is like enhancement load inverter. Okay, so we have already studied this somehow a little bit. We know the fundamental of this one, and and let us try to explain somewhat in more in detail how this kind of circuit works, and how to calculate all the parameters, our required parameter for the enhancement load inverter. Okay, we know that if I have to design an enhancement load inverter, in that case, what I can do, I can simply, if I have connected this gate terminal of the load transistor to the VDD or to somewhat other potential, somewhat higher, then we can say that this will be in the, and this is the nothing but enhancement load. Okay, so what I am doing, I'm just connecting this with the same VDD, whatever we have. So this will become the enhancement. Now let us try to see how this circuit will behave. Okay, and before that, let me write some name and other things so that you will be able to. So this is nothing but this is the ML. ML means the MOSFET at the load side, and MD I am writing here, which is the at the drain side. And let us try to write something like here we have some load capacitance which we have connected, which is the CL here. Okay, and here we have provided input and something like that. Now let us try to see, let us try to validate how this will look like. Okay, so suppose if I can have a two possible combination of inputs, like see, so V in, and let us try to write ML, MD, and then let us try to see what is the V output. Okay. Now I can have two possible combinations. The first combination, like the input can be 0 or input could be 1. So this is the two possible way which we can have. Okay, so if in the case if input is equal to 0, this MD will be in off state. So this MD will be in off state, and because ML, the gate of this ML or the load transistor is connected to the VDD, so this is always in on state. Okay, so this ML will be in the on state. Okay, so see if you can see here, ML is in on state and MD is in off state. So we will get a path which is something like this. So this is the path on which this capacitor will be charged. Okay, so this capacitor will be charged and the output will be high. But the important thing is, because at the load side we have connected we have used the NMOS transistor, and we want to pass logic high by using this NMOS transistor. So we know that because the NMOS transistor is weak high, they cannot pass completely logic high. There will be some threshold voltage drop. So what it means, at the output we will get something threshold voltage drop output. So we were expecting like we will get the output VDD, but because we have used the NMOS transistor, there will be threshold voltage drop, and that is the VDD minus VTH. Okay, so this is the output which we will receive. Now, yeah, of course, this VDD minus VTH is, yes, definitely this is on higher side. So we can say that this is logic 1. Similarly, if we talk about if the input is equal to 1, okay, if the input is equal to 1, in this case, what will happen, because the ML is always in the on state, okay, and MD will also be in the on state. So it will act as a voltage divider from a voltage divider circuit, because both the transistors are in on state, and they will form a voltage divider. Okay, and based on the strength, based on the size of the transistor, either of the ML or MD, the output logic will be. Okay, so here this output voltage, this can be 0, but this is the function of MD and ML. Okay, MD and ML. This is the function of MD and ML. And the important thing is, if the strength of ML is increasing, let me change the color. So if the MD strength is increasing, in this case, the resistance of MD will reduce. And if the resistance of MD will reduce, V out will be close to the logic 0. So V out will be close to logic 0 if the size of MD will be increased. Okay, and vice versa. Like what is the output voltage in case of input is equal to 1? That completely depends on what is the size of the transistor. Okay, so this is
Hello, sir.
Yeah, please.
Sir, can you explain that case 1 V in equal to 0?
V in equal to 0. Okay, so if V in is equal to 0, in that case, what is there? We are seeing like if V in is equal to 0, MD will be in the off state, because the gate terminal is connected to 0. Okay, so MD is in off state, and because I have already provided a gate terminal of this ML to the high potential, what it means, this is always in on state, because this ML is nothing but this is the NMOS transistor. So what because this ML is in on state, what I am expecting that this VDD must be transferred to this V out. But because I am transferring this high logic through this NMOS transistor, there will be some threshold voltage drop, because we have already studied the NMOS transistor cannot pass strong high. There will be always a threshold voltage drop. Okay.
Yes, sir, got it.
So output we will receive like VDD minus VTH, which is close to the logic high. So this is the combination what we are getting. So, and similarly for the second case. Okay, so this is the thing.
Yes, sir, got it.
Try to make the voltage characteristics, how the characteristics would look like the transfer characteristics. So let us try to see it. Okay, so yeah, before that, let me try to draw the equivalent circuit of this one. I think equivalent circuit is not needed, you know the thing, so I don't need to spend too much time. Okay, so let me try to draw the transfer characteristics, how this will look like. Okay, let us assume this is the V in, and here we have the V output. Okay, and I am giving some input which is changing from here to here like a ramp. Okay, this is what we are changing the input. So let us try to see what is the output. Okay, we know that the maximum output or the maximum voltage, output voltage, can never cross VDD minus VTH. Okay, so this voltage, whatever we have, this is nothing but this is VDD minus VTH. Okay, and how the behavior will look like? Initially, it will act as like if the input is low, then output will be VDD minus VTH, and if the input is 1, it is crossing some threshold voltage, then it will become somewhat lower. But the important thing is that completely depends on the size of the inverter. Okay, a size of the transistors. Okay, so let me draw initially this diagram, something like this. Okay, this could be the diagram. But what happens? This is the case when MD is increasing. Okay, so let me try to make 2-3 diagrams, 2-3 lines, so that you will be able to understand what I am saying. Okay. Another could be like, okay. See, can anyone tell me, we have the 3 different graphs. One is the green, second one is the brown, and the third one is blue. If I will increase the size of MD, like W by L of MD, then which graph will reflect? Like towards to the blue side or towards the green side?
So towards to the blue side.
Towards the blue side, yes. Because the strength, if I'm increasing the size of MD, so the resistance of this MD will reduce, And if the resistance of this MD will reduce, the voltage drop across this one will also reduce, means this will be more closer to the ground side or more closer to the logic 0 side. So the important thing here is, like, if I am increasing the size of MD, okay, so this will shift in this direction, like MD divided by ML. Okay, so if MD by ML ratio is increasing, what it means, the waveform will look like more like an inverter. Okay, so if I have to get the inverter kind of characteristics, I need to increase the size of MD. So this is what the characteristics is. Okay, so this is the transfer characteristics. Now let us talk about how this the equivalent circuit will look like. Okay, so if we see here, the equivalent circuit can be like, if V in is equal to 0, in this case the equivalent circuit is something like this. Okay, and this is what we will observe the output. And if V in is equal to 1, in this case it will act as a voltage divider. Here we will get the output voltage something like this. Okay, and this is the R on of ML, R on of ML, R on of MD. Okay, so if we have the expression something like this, what will be the delay in both the case, like TPHL and TPLH? So let us talk about, let me change the color. So the TPHL, can anyone tell me what is the TPHL? What will be the TPHL? We have some load resistance, so it will be nothing but CL into R on of ML. Okay, so this component depends on sorry, TPLH ML.
So it will be TPLH, right?
Yeah,
Go
so
to
yeah, MD, yeah, MD. Okay, so R on of MD, and similarly TPLH, that will depend on the CL times of R on of ML. Okay, so the important thing is these two components will depend on, like, one will depend on MD and the second one will depend on the ML. And if I'm increasing the sizing, might be this, like if ML and MD are both are equal. Here we have to discuss very important thing. And see, if, because we have both the NMOS transistor, and if the size of both the transistors are equal, in that case we can make equal TPLH and TPHL. Okay, because the on resistance of both the transistors will be equal. And if the on resistance of both the transistors is equal, we can make the equal rise time and the fall time. Okay, but the important thing is, if I have made both the transistors equal, and in case of input is equal to 1, this will act as a voltage divider circuit. And if it is acting as a voltage divider circuit, the minimum voltage which we can achieve, that will be equal to VDD by 2 only. Okay, so here very important thing I am saying, like, just you have to be careful what I am saying. Here we have a trade-off between the noise margin and the delay. Okay, here we can see, like, the noise margin can be enhanced, can be improved by increasing the size of MD. Okay, so this MD, if I'm increasing the size of this MD, the noise margin will be improved. But on the same side, because both the transistors will have the different sizing, this TPHL and the TPLH will be different. So there will be unequal rise time and the fall time. There is a mismatch in the delay component from low to high and high to low. Okay, so the thing is, like, if I have to increase the noise margin, the delay component will be mismatched. They will not be symmetrical. And vice versa. If I have to make the delay component symmetrical, in that case, the maximum voltage which we can achieve that will be the VDD by 2. So let me write it here because this is really very important. If TPHL is equal to TPLH, in this case, the V out will be approximately is equal to VDD by 2. So this is what you can achieve. Okay. So, and this is the problem, like you can maximum achieve the for V in is equal to 1. Okay. And similarly, you can analyze these things. Let us try to make the layout of this one and try to calculate what is the area requirement. Okay. So we know that for the layout, for the VDD, I'm just quickly drawing it with a single line. You just understand there will be some thickness of this one, but yeah, for now I'm just drawing it just like this one. So let us assume this is the VDD. Okay. So, and this is the ground. Okay. So this is the VDD. This is the ground one. Now let us try to make the polysilicon and the diffusion. So there will be some this one for the ML. Similarly, we will have this one for ML, and then for the polysilicon we can have a green line. We can have a green line, and then I need to connect all these components. Okay, so how to connect that one? I have to connect this drain with this one, gate with this one, this with this one. Okay, and I can have this one will be here, and here is the input. Okay, and now I need to take the output from somewhere. V output. Here we have the V input. Okay, and we need some contact points that will look like this one. Okay, so this is what the layout is. Now let us try to see how many layers we have. Okay, so if we want to calculate the layout, so here the first layer is this one, second layer is this one. So in this direction we have 2 layers. Okay, if you see here, first layer is this one, second layer will be this one, third layer will be this one, fourth layer will be this one, and fifth layer will be this one. Okay, so we have 2 layers in the vertical direction and 5 layer in the horizontal direction. Now let us try to see calculate what is the W and L. Yeah, of course we have the layers here, but here we have a gap as well. So gap between 2 things is like here we can see 1, 2, 3, 4 gaps in the horizontal direction and 1 gap in the vertical direction. Okay, so if I just wanted to calculate the W, so W will be nothing but it will be 5 layers plus 4 gap, and we know that the by default we are considering the thickness of this gap, and the each layer is by default, let us consider it is the 4 lambda. Okay, for someone it is 2 lambda, for someone it is 3 lambda, but yes, for the worst case conditions I am considering it is the 4 lambda. Okay, so this W will come something around 36 lambda. Okay, similarly if you talk about the L will be nothing but, if you see here, 2 plus 1. Okay, so here we will have 2 plus 1 into 4 lambda, and that will give you 12 lambda. Okay, now if I have to calculate the area, so what will be the area? Okay, area will be W into L, so that will be the 36 lambda into 12 lambda. Okay, and if the technology node is equal to 32 nanometer, then lambda is equal to 16 nanometer. Okay, can anyone calculate what is the area? 36 into 16 into 12 into 16.
Hello, sir.
Yeah, please.
Sir, the horizontal layer means the horizontal line and vertical layer means vertical line, or what?
Vertical lines means what? Sorry.
Sir, horizontal lines means horizontal layer and vertical line means vertical layer, or what?
Yeah. So layer means like how many layers we have in a particular direction. That's it. So.
Sir, so means like when we are going when we are considering the second horizontal layer, we don't consider that crossover point, or as
second horizontal layer crossover point. Here you're talking, let me use the highlighter. You're talking about at this point?
no, sir, at the
Here?
crossover point.
Here?
First cross, above that.
Here at this point?
Yes, below that.
This one?
Yes, sir. So that
Yeah.
will be 2 or what makes.
No, crossover points that will not be considered. Like, see, here, like how many lines are in the same plane? Okay, it does not depend like how many crossing points we have. So on a same plane, how many lines we have in the direction? Like, see here, in the vertical direction, we have this line and we have this line. In the horizontal direction, we have this line, this line, this line, this and this. So we will consider those things. So these points will not be considered. Like, see,
okay,
see, because this can also be connected to this one. Okay, so it is not necessary to extend this blue line up to this one. Directly I can connect this green line to here. Okay, so you don't need additional layers. You got the point?
Sir, means for horizontal layer, that layers we have to only consider the horizontal lines and number them.
Yeah, yes. Okay,
sir.
fine. So can anyone calculate what is the value after calculating this one? Like 36 into lambda is equal to 16 and 36 into 16 into 12 into 16. Did anyone calculate it? 36 into
Sir, 62208 nanometer square.
62208
nanometer square.
08 nanometer square. Okay, so after calculating these things, we are getting the area which is equal to the 62208 nanometer square. And if I calculate it in the micrometer square, so I need to shift 3 decimal points like 1, 2, 3. So this will be equal to 62.208 micrometer square. So this is how we calculate the area of any layout. This is the way.
Sir,
0.6
10 to the power 6 divided करेंगे ना?
Yeah, what? Sorry.
Sir, can we, if we increase the polysilicon on the PUN circuit, sir, to the VDD, sir, VDD, then
Yeah.
can we decrease the layer ones in?
If we increase, sorry, which policy? Okay, so you are talking about the first. First, this polysilicon, right?
Yes, sir.
Okay, what we need to do?
If we increase up to VDD.
Up to VDD.
Yes.
This one, like you want to say, like this can be extended up to the VDD.
Yes, sir.
But so, the thing is, you need one layer like this now. So you must have some layer for the polysilicon. So even though we have extended it here, it does not depend on the contact point is there or not. It completely depends on, you can do like this. Yeah, just I got your question. Like you just want to make it like the polysilicon should extend something like this. Okay, this is possible, and we can make contact over here. This is possible, but in this direction we need one layer because to make a polysilicon. So in both cases you will get the equal area.
No, sir, but in the horizontal direction, sir, layer 1 can be reduced now in horizontal direction.
This one?
No, vertical direction, sir. In the vertical
direction, na? Okay, so again you will get the same kind of thing. Like, see, this will be one layer, and again this will be one layer. So to make this layer one, you need to have some layer, right? So how you will directly, you cannot make like in this plane. So in this plane you cannot make. Okay, so you need to have a different place where you can connect.
Okay, okay, sir.
Okay, you
Yes.
cannot directly connect from here. Okay, you cannot connect from here. You need some point at which you can do, right? So the
No, sir. I'm just asking that the blue line you have connected with polysilicon upper network,
this
sir.
one.
Yes,
Yes.
sir. It can be replaced with the polysilicon, not
Yes,
by the
yes.
metal.
It can be replaced with the polysilicon, but yes, the area will be same. Like because it required something. Either you can make a polysilicon itself, or you can have this polysilicon and this is the metal. That both is possible. Okay, so you can extend. Yeah, so you don't need one more contact point. Okay, but you need to have a contact point over here, right? So there is no problem. The number of contact point will be same.
Hello, sir. It will be 0.622, right? 622.
Which one?
Area, micrometer square.
Yes, we have to divide with 10 to the power 6 nanometer square to micrometer square.
Nanometer square. 1, 2, 3. No, you're saying like currently we have the area like 62208 nanometer square. And nano to micro, like this is the like this area is like this one. This indicates like per this much of square area. So if you will convert into the micro, so you have to divide by only nano to micro. It will be 3 only, na? You have to move 3 decimal points.
So, but it is square, right?
Yeah, is square. Yeah, but again, I'm considering the micrometer square. So you can calculate like nanometer square and micrometer square. So again, if you see here, just either you can keep the meter square, and micro and nano you just need to convert. Okay. No, sorry, I removed this one. Okay. So as of now, we can calculate something like this, like nano to micro. You have to just you have to shift nano to micro. Yeah, so might be it could be like 0.062, but I need to check whether what need to do. Like I will check it out, and then I will confirm you by tomorrow. Might be someone is saying like area is 110592.
No, sir. No, sir. It was wrong, sir.
Okay, fine. Okay, so yeah, I will check it out whether it should be the micro or it should be like 0.62208 or it should be 62.0. I will check it out, then I will get back to you tomorrow. Okay, as per my understanding, I think I need to just convert this nano to micro, and then we can do it. But the thing is, because we are talking about the nanometer into nanometer, so if I want to convert it to micro, so yes, of course, it should be something like this. So let me write the correct version of the right as of now. And then
Sir, actually, I think I miscalculated. It should be 110592.
huh?
The area, sir, it should be 1 minute.
Can you calculate 32 into 12 into 16 into 16?
Sir,
Yes, sir.
110592.
It would be 110592.
Okay, okay, fine. So let me correct it. So because you have calculated, so I don't know what you have done. Okay, so you are saying 110592. So after shifting 6 decimal places, 1, 2, 3, 4, 5, 6, it will be 0.11059 micrometer square. So this is the area whatever you need. Okay. But I will check it out whether it should shift for 3 decimal or 6 decimal. I will confirm it by tomorrow. No problem. Okay. But
Sir,
okay.
sir, it would be 110. It would 110.292 in micrometer, sir.
110. Like, see, you are shifting by 3 decimal point, right?
Yes, sir. In micrometer.
But the thing is like nanometer square is there in the both the directions. Okay, so I will check it out. There is some. Let me remove this. Okay, so
That's correct.
okay, that will be more better. Like I will check it out, and then I will get back to you. Don't worry. Okay, so this is how you can calculate the area. Now let us go ahead with the new things, like to understand some more fundamental of the things, like how we can calculate the power dissipations. Okay, so what is the power dissipation of this particular inverter circuit? See? Power dissipation. As we know that the static power dissipation is calculated by simply ID into VDD, like V static is equal to ID into VDD. Okay, and if we have something like this, so we know that if Vin is equal to 0, then what will be the static power dissipation, ideal value of static power dissipation? If Vin is equal to 0, in that case, if you can see here in the this one transistor is off state, the equivalent circuit will look like this one. And if equivalent circuit is something like this, there is no direct current flowing between the VDD and the ground. Okay, so I am assuming that ID will be 0. Okay, so ID will be 0 here. So ID is approximately 0. So the P static will be 0. Okay, now let's talk about the second case. If Vin is equal to 1, in this case, both the transistors are in on state. So ID will not be is equal to 0. And if it is not equal to 0, then P static will also be non-zero, which is the problem. Okay, so if you have to calculate the average static power dissipation, in that case, yes, of course, this ID is nothing but this is the function of the sizing of MD and ML. Okay, so that decides what is the value of ID. Okay, so if you have to calculate the average power, in that case, that will be ID into VDD by 2. This ID is nothing but this is with respect to the ID1. Okay, so I'm talking about ID1. So ID1 into VDD by 2. And ID1 is nothing but the current flowing through the circuit when the input is at logic 1. Okay, so this will be the average power through the circuit, average static power through the circuit. Similarly, a very important thing we need to consider here, like dynamic power. Dynamic power is nothing but, if we see here, P dynamic, this is given by alpha F C L V D D square. Okay, we know that this CL is the fix, whatever we have. Alpha is the activity factor, that is fine. VDD is fine. But the important thing, the charging and the discharging time constant and the maximum frequency, that completely depends on what is the delay. Okay, so what is the TD, like rise time and the fall time. If rise time and fall time is very high, so it will take more time to change the logic, so the frequency can also be changed. Okay, so this frequency is nothing but this is the function of MD and ML. Yes, so this F is nothing but this is the function of MD and ML, and by and that decides like what is the value of TD, which we call it like 1 upon total delay. Okay, and based on that we can decide the frequency. So
excuse me.
Yeah, please.
So is that the frequency will be dictated by the maximum delay?
Yeah, that will be maximum delay. So it depends on which of the transistor we are considering. Like see, if the size of MD is very high. Let me go back to the previous slide. So if the size of MD is very high, What it means, the R on MD will be less. R on MD will be less means the TPHL will be less. So in that case, TPLH will dominate on the frequency calculation and the vice versa. Okay, so whichever is the highest TPLH or TPHL, that will decide what is the maximum frequency. If both the transistors are equal, in that case, the TPLH and TPHL will equal. So in that case, the frequency will be that one. But yes, as you told, like, yeah, this is correct. The maximum delay will be considered as a to calculate the delay, to calculate the frequency of the operating frequency of the circuit, right? You got the answer?
Yes, sir.
Okay, fine. So this frequency is the nothing but this is the function of either of MD or ML, whichever is larger, that will decide what is the value of TPHL and TPLH, and that will decide the delay, and based on that we can calculate. So this dynamic power, this is how they are function of each other. Now let us talk about the noise margin based on the transistor sizing. This is really very important graph that I'm going to plot. And suppose I just want to calculate the noise margin. Okay, so the noise margin can have two possibilities. Either MD is dominating or ML is dominating. Right, I have already told you, like the size of this MD and ML that decides what is the noise margin. If both are equal, in that case, the minimum voltage that can be achieved up to VDD by 2 only, not more than that. Okay, but if I keep on increasing the size of the lower transistor, which is the driver one, okay, here we can say, if I'm keep on increasing the size of MD, the noise margin can be increased. Okay, so let us try to relate all those things in a single figure. Okay, so let us assume this is the input, this is the output. Yeah, let me draw one more characteristics. Okay, V in, and here we have the V output. Okay, now I'm considering the first circuit is for weak MD. No, don't write here. Okay, and the second figure I'm considering for strong MD. Okay, and let us try to make the characteristics. Okay, can anyone tell me how the characteristics will be different in both the diagrams? If I have the
for
weak MD,
the noise margin will be lesser.
Where noise margin will be lesser?
Sir, for weak MD.
In the weak MD, yes, perfect. So the characteristics which I will receive will be something like this. Okay, and for the other case, I will get the waveform something like this. Okay, and we know that, yeah, let me make it perfect so that something like this. Okay, here we have. Now let us try to check what is the VOH, what is the VDD, what is the other things. Okay, so let me try to make those things. This point is nothing but this can be maximum, that will be the VDD minus VTH. Okay, VDD minus VTH. This is also like VDD minus VTH. Okay, if I'm talking about the negative -1 slope, so -1 slope will be somewhere here. Similarly, for this, I need to calculate the -1 point. So let us assume this is the -1 point. Okay, and this is also the -1 point. So this is nothing but -1 point indicates what is the value of VOH. Similarly, this is also the VOH. Okay, let me make it perfect, because -1 slope I cannot see from here. Yeah, let me, yeah, so just assume this is something like this only. Okay, other things, if I have to draw, like what this value is, can anyone tell? What is this value? VIH?
VIH.
VIH or VIL?
It is VIL, sir.
This will be VIL. So let me
VIL.
draw the second. Yeah, wait 1 minute, please. Let me draw the other -1 point, and here is the -1 point. Okay, and here one crossing point here. We have one crossing point over here, and the minimum value which we can have, one will be here, and the minimum value we will be here. Okay, so just let me know which one is the VIL, VIH, VOH, whatever. So VOH we have, and this is nothing but VOL. This is also VOL. This one is the VIL, because this is a lower value, right? So I need to write VIL, and this is the VIH. This is the VIL and VIH. Okay, so this is how it will look like. So let us try to come up with the conclusion. What is the conclusion? If I am making the driver transistor stronger, this VIL will be lower. So VIL will be lower, will be shifted in the yeah. So let me summarize somewhere. If MD is increasing, okay, if MD is increasing, what is the impact on VOH? What is the impact on VOL? What is the impact on VIL? And what is the impact on VIH?
Sir, I think VOH is remaining same, VOL is decreasing.
Okay, so VOL will reduce. I am holding the VOH. Okay, now the VIL, if you see here, the VIL will be lower if I am increasing. Okay, because this will shift in. Yeah, so if we can go here, this waveform is shifting in the left side, so VIL will be shifted in the left side, so it will reduce. Okay, so the VIL will be reduced. VIH, yes, of course, VIH will also reduce. Okay, and what about the VOH? Okay, so let us go back to this slide one.
For VOH will also decrease.
VOH will
decrease.
Okay, so the -1 slope, wherever the -1 slope is, that will also be reduced. Okay. So this is how we can calculate the noise margin and other things. Okay, so noise margin you can calculate, and optimal noise margin you can have. Okay. Next one is the pseudo Nmos inverter. Okay, so pseudo Nmos inverter, let us try to understand how the pseudo Nmos inverter looks like. If I am connecting this gate terminal of this PMOS transistor to the ground, in that case it will look like this one. Okay, and let us try to make the truth table of this one. Like we can have a V input, and then we can have the, yeah, let's write, this is the ML, this is the MD. We have connected some gate load capacitance CL. So V in ML, MD, and V output. Okay, and let us try to calculate it. If V in is equal to 0 and 1, if V in is equal to 0, in that case MD will be in the off state, ML is in the on state.
Sir, ML is always on.
Yeah, so ML will always, in both the cases ML is on, and MD will be in on state if input is equal to 1. Now let us try to check the output, right? So here V output will be like what is the V output? Can anyone tell me what is the V output if for the first case?
First case it will be VDD.
VDD, yes, perfect. Yeah, so the advantage of this circuit over the previous circuit will be like in the previous circuit we were getting some degraded maximum voltage due to the NMOS kind of load, but that problem can be overcome by replacing that NMOS transistor with the PMOS transistor, and that we will get the maximum voltage will be VDD because we have connected the PMOS transistor over here, and the PMOS transistor is nothing but this is the strong high, so we will get the output which is equal to VDD. Okay, now let us talk about what happens if the input is equal to 1, because both the transistors are on. Okay, if both the transistors are on, now this output becomes the function of MD and ML. Okay, and if I am increasing the size of MD, then the V output can be, we can have it close to 0, something like that. Okay, so size of MD that decides what is the lower logic here. Okay, so let us try to make the characteristics of this circuit. Okay, so the characteristics will look like this one. Okay, let us assume the initial characteristics is something like this. Okay, this is nothing but this is the VDD. Okay, what happens if I'm increasing the size of MD? Okay, so if I'm increasing the size of MD, so yeah, so let me draw the different characteristics. Okay, something like this. Okay, so can anyone tell me where the waveform will shift if I am increasing the size of MD? If I am increasing the size of MD, where the waveform will shift? Yeah, of course, I have already done over here. Right. So if I am increasing the size of MD, so MD to ML ratio will give something like this kind of response. Okay, so this is how you can calculate. So this is the waveform for this one. So the important point over here is like this VIL will shift just like a previous case. Okay, so VIL will shift, VIH will shift, VOL will also shift, but VOH that can also be shift. Like so, you based on that you can calculate what is the noise margin. Yes, if you see here that the power dissipation in this circuit is same like the previous circuit, because in one case the power dissipation cannot be 0. Like in the second case, if the power dissipation cannot be 0, like so in that case this design is not the power efficient. Okay, so P static 0 is approximately 0 as ID will be 0, but P static for 1 that will not be 0 as ID is non-zero. Okay, so this ID that depends on the size of this ML and MD. But can anyone tell in terms of area, which of the I'm not talking about in terms of area, which of the arrangement, like pseudo NMOS arrangement or enhancement arrangement is good? Okay, can anyone tell? In terms of area, which of the circuit is good? And in terms of noise margin, which circuit is good? Because both circuits performing like same, like both have the same kind of characteristics. You need to increase the noise margin, you need to increase the size. Okay, but the important thing is, like, if you have to increase the noise margin, the pseudo NMOS will be considered, because the maximum voltage in the second case, like in the pseudo NMOS case, will be the VDD, but in the previous case it was not VDD, it was VDD minus VTH, so the noise margin was less. Okay, so if your concern is the noise margin, in that if you are comparing these two circuits, so in case of noise margin, the pseudo NMOS inverter will be better as compared to the enhancement load inverter. But if your target is like area, so important thing is, like, to make equal ML current flowing through ML and current flowing through MD, you need to increase the size of ML by approximately 2.5 times because of the mobility change. Because in the PMOS transistor, holes will be there, in the NMOS transistors, electrons will be there, right? So to match both the currents, you need to increase the size of ML at least by 2.5 times, so that you can get the equal current flowing through both the transistors. Okay, so you need to increase the size of PMOS transistors over here. But in the previous case, because both the transistors were NMOS transistors, so you don't need to increase the size of the load transistor. You can keep both the transistors equal. Okay, so here, to get the same current strength, same current drivability, you need to increase the size of ML by 2.5 times, and that will increase the overall area. Okay, and this is the problem here. So in one terms, we are getting the benefit, like we are getting the better noise margin. Yes, of course, the power dissipation will be approximately same in both the cases. But if you are talking about the area requirement, the area requirement in pseudo NMOS will be larger, higher than the enhancement load inverter. You got the answer or not? You got the point what I'm saying? Can anyone acknowledge? Okay, so this is the important thing which we should. Ajay, you want to say something?
So sir, which one do we really use?
Yeah, so the important thing is, it completely depends on your applications, right? If your concern is the area, in that case you will consider the previous one. And if your concern is the better stability, better noise margin, in that case you can go for the pseudo one. But in practical, none of these circuits are used. Okay, so which of the circuit is used, I will explain tomorrow. Okay, so in practical, these two are not good, right? So they can have the power of the problem of power dissipation, they can have the problem of the noise margin. But to overcome these both the things, you can have one more circuit, and that circuit is the CMOS inverter. Okay, so we will discuss more details about the CMOS inverter in tomorrow's lectures. So I'm closing the session here only. In case of any doubt, you can write email to me. Thank you so much.